Hello, I'm Bart Stock. Today we're going to be talking about the evolution of the computer industry, how its structure has changed over time. And we're going to start at the very beginning with Alan Turing and then go forward to the present day. So bear with me. I'm going to switch over here to the presentation. Here we go. And you can see I spent 8 years at MIT as a student, and I have a bunch of 30 odd papers that I published that are in referee technical journals, as well as a book that was put together as part of a computer science master's curriculum at Bell Laboratories. We also taught it at Columbia for 3 years, 3 semesters. And this involved giving talks at over 50 universities and research institutes in North America, Western Europe, the Soviet Union, and Japan. So here we go. Our outline is going to be, we start in the 1940s with the foundations of what became the modern computer industry. In the 1950s, we saw the first commercial electronic computers. The 1960s, IBM launched System 360. 1970s was the decade of mini computers with Digital Equipment Corporation, Hewlett Packard, Wang, Fujitsu Prime, NEC, many others. For example, Data General, a spinoff from DEC. 1980s, we saw personal computers, Apple, IBM, Tandy, Commodore, on and on. And then we'll go into some software. And that leads us up to the development of Unix and how Unix influenced a lot of things that have happened since then. So Unix is an operating system developed at Bell Laboratories in the 1960s, 1970s, and it took on a life of its own, to put it mildly. So here we are. We're going to start with Alan Turing, shown here, incredible individual who, among other things, led the code-breaking activity of the German Enigma machine and World War II. George Dyson wrote a masterful book on Turing and what he did. And one of the key things that Turing did at the very start was he took a huge amount of incredible mathematics and even philosophy and turned it into a mathematical model of computation that described an abstract machine. You manipulate symbols on a strip of tape according to a table of rules. And this summarized all of this incredible body of knowledge that have been developed in logic and in philosophy. And yet it is still true today that the simple model can implement any computer algorithm. So what in the world did he come up with? Well, here we have a model of a universal Turing machine, and it shows here's an infinite tape at the very bottom with symbols on it, zeros and ones. There's a state transition diagram. So the system goes from various states. Say it starts off in state 1, it'll go to state 4, and then that's it. It'll go from state 1 to state 3, and then to state 5, and then it'll halt over here, and so forth. So the Turing machine will go look at these different symbols, and based on the symbols, we'll move the tape to the right or to the left and replace the symbols accordingly, according to what the state transition diagram says to do. So there we go. Incredibly simple, but what happens? Well, John von Neumann built on what Turing came up with and came up with an abstraction of a computer that actually is the same as what we just saw, but is in some sense much more useful. The computer consists of input devices, output devices. They could be, the same device doing input and output. There's a memory unit there that stores everything. And then there's a processing unit that controls things, and then it has special units for doing logic and arithmetic. Now, what's hidden in this picture is that there's in fact a switch fabric, something that interconnects all of these different things here so that they all work together. So in the IBM 360, IBM built what was called a channel that allowed all of these different devices to interact with one another. Digital Equipment Corporation made a unibus that had all of the different devices we're talking about here connected to one another. And so it goes. So this is a critical part. I don't want to minimize it, but it doesn't show up here in this picture. So in the 1940s, there was really a huge impetus from the military during World War II for artillery, for having better ways to target where they're aiming guns of different sorts. Radar was developed. So then the question was, how would you be able to determine how far something is from you? How fast is it moving? And then, of course, at the end of the war, there were nuclear bombs, and this required incredible amounts of computation to figure out how to, if you will, build better bombs, simpler, smaller, whatever they were. Different groups in the US and in Western Europe worked on this activity. And what was unusual was John von Neumann, who was an incredible pure mathematician at the Institute for Advanced Studies in Princeton, ended up getting fascinated with this because he could see as a mathematician that the computer would allow him to deal with real world problems, not toy problems, that there would be sensors that would gather data from the real world, and he could build models that would be in the processing unit, and then they could be able to carry out very complex calculations involving integral and differential equations of various sorts, among other things. In fact, new sorts of equations. And that at the end of the day, he'd be able to advance mathematics by carrying out experiments on theorems, on is this really true? He could try out a bunch of things and get a good idea for what was true and what wasn't true. And he was fascinated with this, but the end result was that the Institute for Advanced Studies really just focused on support of things like pure math and pure theoretical physics, and not something like building hardware, electronic hardware. So von Neumann at the end of the day gave this design work that he'd done to IBM, and IBM turned it into a product called the IBM 650, its first electronic computer. The basic hardware modules, as we said, were a processor. There was memory. There was a hierarchy of memory because you wanted as much memory as you could get, but fast memory cost a lot of money, and slower memory, things like tapes, for example, were much less expensive, but also much slower because you had to wait for the tape, had to move to wherever the data was that you were looking for on the tape. Then there were a variety of input and output devices like printers, modems, terminals of different sorts. And as I mentioned, this switch fabric or bus interconnection. So the programs that were written here in the 1940s were really all written in what's called machine language or assembly language, involving ones and zeros that the machine could directly execute. So in the 1950s, what happened was we had commercialization of these raw ideas. The original computers were built with vacuum tubes that involved they threw off a lot of heat, and the end result was that the vacuum tubes would run for thousands of hours, but then fail. And this led to a big impetus to come up with things that function the same as vacuum tubes for switch elements. And this led, in fact, to using transistors, solid state switches that consume dissipated far less heat and therefore led to far more reliable computers. The end result of this is something like the phone that you have in your hand today. It has literally billions of these switch elements in them, transistors, and yet doesn't overheat and is highly reliable. But that's down the road a ways. The basic storage here that was used was based on magnetic cores. So wires were wrapped around a toroid, a magnet, and these were interleaved in a way, so you had an array of magnets there that was storing all of this information, and then you had to have circuitry that could go through this array of magnets and find the core that had the information that you're looking for. There were also other types of magnetic storage devices like drums and what became disk drives and tapes. And of course, there was punched paper where terminals would have the ability to punch paper tape. And then you could store your program on this and then read it back in, or you could put your data on this and read it back in through the paper tape reader. So it was an input-output device. The software for all this was using Fortran for formula translation, Fortran. There was BASIC, for example, which is developed in education at Dartmouth, Lisp, which was developed for actually Lisp processing systems. And then there were very early operating systems that showed up here. Bell Laboratories developed an operating system for the 650, and IBM was given to IBM. IBM chose not to commercialize it because it used up a significant fraction of memory, and a significant amount of the processing cycles went to the operating system. What IBM missed was that the programmers were far more productive using operating systems rather than programming in assembly language, but that came later, as we'll see. So IBM developed a whole series of things following off the 650, going from the 704, 709, and so forth. Burroughs developed its own independent line of computers that were in many ways superior to what von Neumann had come up with. Their designer there had a lot of ideas about how to do things in parallel using concurrency that led to some very innovative designs. We had UNIVAC, controlled data. General Electric was a major player. Bull in France, ICL in England, and Fujitsu in Japan. So these are all examples of who was there in the 50s. In the 60s, what happened was transistors finally kicked in, and this led to a huge change, moving from having vacuum tubes to having solid state logic. The magnetic core storage increasingly was replaced by transistorized memory, both static and dynamic random access memory. But the magnetic storage still was there because it was incredibly cheap to get large quantities, and this showed up on magnetic disk drives and tapes here. And then the terminals that were there continued to evolve to be more and more capable. The software that was involved, IBM developed its own programming language 1, PL1. We still had Fortran, COBOL. IBM developed a transaction manager called Information Management System, and a database management system, Information Management System, and a transaction manager, CICS, the Customer Information Control System, that managed things for like banking transactions, for example. And then the 360 line of computers had the OS 360 operating system. In contrast, Multics was developed with General Electric doing the hardware, Bell Laboratories doing the software, and MIT doing a lot of the design work on this. And Multics was actually commercialized by GE. There were probably, I want to say, 20 systems that were actually sold. But the key thing about Multics, about citing it here, is that it led to a stripped version, which we called UNIX. So the thing about UNIX was simply that Multics had too many icks and UNIX had one ick. That's the joke. The other thing that came up here was, and this is fundamental, was the notion of interfaces and an architecture that was the system of interfaces that defined how the different modules would interact between one another. So this provided the modularity that was needed to do modules and test them to make them be highly reliable. And once all the modules were tested and were working, then you would start to tie them together in system integration testing. And when things failed, you knew right away, well, we just added this one module, and therefore that's where the fault is. So things related to fault detection and isolation of faults and then recovery from the faults led to much more reliable systems, but this also allowed you to manage incredible complexity. So the basic idea here would be if you had, say, 5 modules and each had, 100 states in them, actually then when they interact with one another, I have 100 times 100 times 100 times 100 times 100, or I have 10 to the 10th, 10 million states that I could possibly be in out of 5 modules each with 100 states. And this is what made it possible to handle the real world issues that you faced in computers when things didn't behave the way you wish they would. So the architecture here, the notion of architecture, is a specification of all the interfaces between all the different subsystems here. And this is a very simple idea, but it was missed early on by a lot of very smart people. But this allowed really to have better estimates for staffing. How many people would you need to develop different modules? Who was involved in integrating the modules, testing the modules, and so forth. So it became much more of an engineering discipline. In the 1970s, we went to mini computers where, again, transistors continued to shrink in size. More and more transistors are on a single integrated circuit, and increasingly transistors are used for the basic storage of the processor. Magnetic storage continued to evolve. And here, for the first time, we see UNIX appearing. UNIX was developed, again, as a stripped version of Multics, and it ran on initially digital equipment computers, but then over time ended up running on anything else you could think of. In 1975, Ken Thompson, who developed UNIX at Bell Labs, went to Berkeley, and Bill Joy, who was there at Berkeley, took a tape that Ken Thompson had, and he developed a Berkeley version of UNIX, which spread all through Silicon Valley. So all of the different computer companies, Silicon Valley, like Hewlett-Packard, for example, and the many other ones that were there at the time, all needed an operating system. And here they had UNIX, which they actually had source code for that they could run with. IBM was a player in many computers with its Series 1 and in System 34 and System 38. But they were targeted after particular applications. So IBM typically targeted accounting applications. Hewlett-Packard targeted applications related to measurements and monitoring things. Digital equipment was into factories and into engineering activities and companies. Wang was into word processing and so forth. So you could see that each of these mini computers was targeted at particular areas, which allowed each of them to grow very rapidly. But the surprising thing was they didn't run into one another. There was very little overlap, and it's because the applications that developed for the accounting side really weren't too useful for the engineers, that use digital equipment computers, and the digital equipment computers had all kinds of engineering software that wasn't too useful for the accountants, and so it goes. So ultimately, it was the software that was selling these things. We get to the 1980s, personal computers came in, where you could finally get something that was your own personal computer. There were those based on the Intel 8086, such as the IBM PC, Apple with its Macintosh ran with the Motorola 68,000. Zilog was in there with a series of processors as well. The number of transistors continued to grow. The amount of magnetic storage continued to grow per device. And we had now Unix running on this, but also a variety of other operating systems. There was CP/M and DOS. DOS ran on the IBM PC and became de facto a market standard. You had applications like VisiCalc, a spreadsheet, WordStar, a word processing program, Ashton Tate, a early database program, and Oracle that was a relational database, all running on these things. And the vendors here are who they are. So you'll notice that in every era, it seems that the companies change, with a change in the basic technology, from mainframe computers in the 60s to mini computers in the 70s to personal computers in the 80s. There's a new set of players. Like digital equipment really is not a player here in this list, but it was a major player in the 70s. So this led to a brand new business model with personal computers, where what IBM had done was they published the standards for the bus, the industry standard architecture bus for the PC, and anybody could go buy a processor from Intel in 86, 88, and you could license the DOS operating system from Microsoft. And so you were off to the races, being able to put together everything that you wanted on your own. So the value that was there really in the earlier days, in the mainframe and mini computer days, the system integrators really had all the value because things were closed. You had no choice but to use things that were met DEC standards, and a lot of times DEC was not forthcoming, so DEC made a lot of money. You couldn't go anywhere else. Same thing with IBM and all the other vendors. But in the personal computer business, the main difference here was that the open standards meant that the Intel with its processor and Microsoft with its operating system software really had all the value, and the rest of the things became commodities, the bus and all of the add-ons and so forth. And people would come up with different wrinkles, different peripherals, but gradually, if they were successful, they'd get commoditized and everybody else would have them after a while, except for Intel and Microsoft. They were in there. So we have an interesting statistic to me. The actual peak year of growth rate in shipments of mainframe computers for the mainframes was really the first year that IBM started shipping 360s in 1965. 7 years later, the peak year for growth in mini computers with DEC, Hewlett-Packard, was 1972. So the technology had advanced sufficiently so that mini computers could do tasks that would have been run on mainframe computers in just 7 years. The economics were such that something that would cost $10 million could be run on a computer that would cost $100,000. And when we got to personal computers in 1979, the same thing could be run for $1,000 personal computer. So just shows the power of the advance of the underlying semiconductor technology, and also the storage. This storage was advancing at the same rate. 1986, Sun Microsystems and other companies introduced workstations, and this was their peak growth rate. And then mobile phones appeared, and the peak growth rate for mobile phones was in 1993, and that's where we're at today. The mobile phones continue to grow in capabilities, and there isn't anything that we see beyond this. So again, what were the innovations that changed the cost benefit here? We went from microprocessors that allowed tens to hundreds of transistors to tens to hundreds of billions of transistors. We had general purpose processing units that were key to allow a lot of very time-consuming algorithms, things like matrix inversions or fast Fourier transforms, things like this, to run very fast. We had lots of software written in things like Fortran. We had an operating system, and as we pointed to Unix, today, for example, if we looked at the phones that are out there, there are Android phones and iPhones, and the Android operating system on the Android phones is a direct descendant of Unix, and the operating system on the iPhones is a direct derivative of Unix, a different derivative. And then the final thing that kicked in here was we had the World Wide Web. So we had a web browser that appeared, and that led to a change in having networking, connecting everything. What about software now? We're gonna leave the hardware side of things and turn to software. First operating system that anyone knows of was done by Vic Vysotsky and Dick Hamming at Bell Labs, and they wrote this for the IBM 650. Gave it to IBM, and as we said, IBM chose not to commercialize it because it chewed up a lot of processor cycles in memory. But as we also said, people were far more productive, and so it didn't go away. It just ended up becoming less of a hog in terms of processor cycles in memory. The Defense Advanced Research Projects Agency funded Multics in 1964. And Bell Labs, while I was working in this, chose to pull out in 1969. And Ken Thompson took the ideas of Multics and developed Unix on a digital equipment, PDP 1145, which he programmed in assembler. And Dennis Ritchie worked with Ken Thompson and developed the C programming language, and then went ahead and re-implemented Unix in C in 1973. C is viewed as a high-level language because it supports a lot of interesting ideas such as pointers and other concepts. The other thing about C, though, as a high-level language is you can actually mask on bits. You can, which is very useful for writing device drivers for things like peripherals, like disk drives and so forth. So C was an interesting engineering compromise. It was both high level and then low level at the device driver level. As I mentioned, Ken Thompson took a copy of Unix to Berkeley, and Bill Joy ran with it and spread all over Silicon Valley. And there was a major change here, going from procedural programming to object-oriented programming. Procedural programming, you'd view things as a series of tasks. You do this, then that, then the other thing. Object-oriented programming was very different. You had a series of objects that would send messages between one another, and that was the only way they could communicate. And this allowed, by having the right set of objects, you could build far more reliable and far more scalable software than you could with procedural programming. The problem with procedural programming was that every time you made a change to something, and you were always making changes, additions, fixing bugs. You had to go back and go do regression testing to go see what in the world didn't work now after you touch something. In object-oriented programming, each of the modules had fixed interfaces. So when you changed a module, if it didn't work, you'd go back into that one module. You knew exactly where to go and fix it. And this made everything go much more quickly and much more reliably. So here we have a little graphic of the evolution of Unix. Here's a picture of Ken Thompson, Dennis Ritchie, 1969. And we go forward all the way. This goes up to 2015 here. And Unix is still going strong. It's the core, the variant of Unix today that runs on the servers that make up the web that we use literally every day. So again, the short history of Unix started with Multics running on a GE 645 hardware. The main problem with this Multics was it used paging memory, that there were a set of pages of memory and your program would have to have those pages in main memory. Typically, you had lots of people using a computer, so many terminals were attached, so that the memory that any one person wanted at any one time was probably not there in memory. It was probably off on a disk storage. So you had to wait for the disk to pull your pages in before you could run. And the performance of this was such that it was really tough for people to use this. Unix didn't have any paging whatsoever. It had just assumed that everything was in memory, period. And that's why it was viewed as a much smaller a Unix as opposed to a Multics. But this was also, the gift that we have today. If you look at your phone, for example, there isn't any disk drive. So you just have a huge amount of memory on your phone and everything fits into it. And that's the end of the story. The key thing about Unix to keep in mind here was it actually was ported from one platform to another in 1978. In this case, they went to a mini computer from Interdata. So there'd never been a program as complicated as an operating system that had been ported from one platform, like the digital equipment platform, to another. And Unix carried the day. And then that's why it spread all over Silicon Valley, ran on everything. The different versions of Unix that were produced were all referred to as research Unix because Ken Thompson and Dennis Ritchie were in the research area, computer science research at Bell Labs. But then there was an actual license given to University of Illinois at Champaign-Urbana. And this ended up spreading across all these different universities because the universities could now lay their hands on source code and could actually teach people about what it meant to do things with operating systems hands-on rather than, in some toy sense, okay? And so there was a surge here from 1975 to 1985 of just the adoption of Unix by all kinds of startups everywhere. In the 1990, it became the operating system of choice for over 90% of the world's 500 fastest supercomputers. If you go look on the website, top500.org, you'll see a list of every 6 months it's refreshed. These are the 500 fastest computers in the world, as judged by the fact that they have a set of benchmarks that they have to execute. And they look at the times, and whoever has the fastest time is first, and whoever has the second fastest time is second. And Unix just took off and took over everything. It also helped that Sun Microsystems was highly successful in pushing Unix out into the commercial marketplace. Apple was active with Unix, and this derivative of Unix that they had became the core for the Mac operating system. called Mac OS, and iOS is the derivative of Unix that runs on the phone for Apple. And so when we look at this, we find that Unix-like operating systems are used in the servers that we find on the web and on mobile devices and on what we would call workstations or tablets and so forth. So what is it about Unix that makes Unix so successful? Well, there's a modular design here, and this is where small is beautiful. The operating system provides a simple set of tools. Each performs a limited, well-defined function. And so this is very much something of a work of art. What are these core functions you need? The key thing that Unix has is a unified file system, which is really the guts of Unix. The one thing that's probably unique about Unix is it has an inter-process communication mechanism known as pipes, whereby one program can pipe information to another program. So the output of that program is the input to another program, and you can set up a pipeline of programs. And I'm not aware of any other operating system that has this notion here. It's all made possible through the use of buffering. Unix had a command interpreter or a shell, and over time, the shell evolved in terms of what it could do. So you could write whole applications in the Unix shell, and there were all kinds of tools available for doing things. It was the first portable operating system in that it ran on different target hardware. Everything was written in the operating system, virtually everything in C. So if you had a C compiler, then you could get Unix up and running very quickly on whatever computer that you had, and that carried the day over all the competition. Unix was originally designed by people that were experts in software. And since they were building software, they wanted to have the best software development environment they could come up with. And so that drove the design of Unix over the initial period of time, 75 to 85. There wasn't really any design intent for it to be portable or to support things like multitasking or where you have with servers today, where there's a huge amount of concurrency occurring. That all came after the fact. But Unix gradually gained these capabilities of portability, multitasking, and multi-user capabilities that we're quite familiar with today. So the idea was to use plain text for storing data, to have a hierarchical file system. You treated devices and certain types of inter-process communications just as files. And so they go into the file system. And then there were a large number of tools, small programs that were strung together using pipes, for example, so that you could, as opposed to building a single program that was monolithic, you could put it together with modules. Because of all this, this created the need for a standards activity. So different companies in the computer industry, hardware, software, got together and created POSIX. The IEEE was active in this, and there's a bunch of other activities here that led to standardization of Unix and today things like Linux. So now let's go into a little more detail about the structure of Unix rather than talk about it at a high level. Deal with the kernel, the actual core of the operating system that does everything, the development environment, the commands, the documentation, and the tools. And in all of these areas, Unix has evolved significantly. So the kernel provides the services to start and stop programs. It handles, for example, there's a scheduler that avoids conflicts when programs try to access the same resource or device simultaneously. There's an actual priority mechanism here that kicked in. So things that were short in time would run quickly, and things that were long in time simply would take longer to run, but they would take long to run anyway. There was a file system and a lot of other low-level tasks that most programs shared. And the kernel, as a result, had special rights that were reflected in what was called the kernel space of memory, which is different from user space. And the current user space was lower priority, and the kernel space was higher priority in terms of controlling what ran when. The kernel has a source code in a directory, user/sys, and if you look in this, you'll find several components. There's a configuration and machine-dependent parts, including the boot code. There's the device drivers for controlling the hardware and pseudo hardware, the operating system, kernel handling, the memory management, process scheduling, system calls, and then header files to define the key structures within the system and important system-specific alternatives there. So it's simple deceptively, but it was the right balance. It was enough complexity, but not too much. Other people got carried away with more complicated things and never got the popularity that Unix enjoyed. And so it goes. In the development environment, the early versions of Unix contained a text editor, ED. There was a C compiler that showed up, a machine language assembler for the machine, a linker for combining different object files, then a library with a lot of object code for C runtime support, but a lot of additional libraries for things like mathematical functions or database access. So there was, Unix introduced one of the first versions of what would be called a standard IO library. The development environment, well, here we have the IO library as part of the system library. And this is just mushroomed. There's huge amounts here. There was Make, which was a build manager. So you would be able to take these different modules and build up a release of software, and you could keep the release. Make would keep different point releases there. So whenever you had any problems, you could always roll back to the previous release that worked while you troubleshoot the release that didn't work and find the problem and then roll forward to that. There were include or header files for software development that gave standard interfaces here. And then there were other languages beside. There was a Fortran 77 compiler here. There was an awk, a scripting language. Awk stands for Aho, Weinberger, and Kernighan, the three individuals that put awk together. And then there are many other things. So for example, Pascal showed up. There was a new compiler collection. There were lots of other tools, symbol tables, compiler development tools. We have Lex here, a lexical analyzer that Mike Lesk and Eric Schmidt, who became then at Sun Microsystems and went on to be chairman of Google. Eric Schmidt did Lex, and Yak with Steve Johnson, yet another compiler. So you could front end, you could take your whatever language you had, and with Yak convert it to C, which would then run because the C compiler was at that point bulletproof on all of these different hardware platforms. The commands here are interesting. Unix makes a little distinction between commands. For system operation and maintenance, there's user commands and system commands. And so, for example, a system command would be the clock, CRON, cron, or the commands of general utility, for example, general grep, general regular expression pattern matching. And then there are more general purpose applications like text formatting and typesetting. But having said all that, the fact that there's little distinction between them We can see there's a shell, which is the command line interpreter that is there. There are all of these utilities that Unix has for doing all kinds of things. There are administrative utilities and user utilities that go on. Things like passwords are a user utility, as an example. The commands in Unix, let's go into those a little more detail. Document formatting, Unix systems were used at the outset for document preparation and typesetting. So the actual commands in Unix are available online as part of Unix as manual pages. You don't need to have some pile of paper sitting around. And whenever there was a change in commands, and that was updated immediately. There were all kinds of things for text processing. The book that I co-authored was written with TROF, text runoff processor. It used table, it used equations, and there wasn't any. The one problem I had was there wasn't any paint type program available at that point in time. Now there are myriad programs, but all of these things are there. There was a lot of support now for graphics because graphics finally became cost effective. As memory got cheap enough, you could map every point on a display to a set of bits. So you had a bitmap display, and then the bits could take on different attributes like color, for example, and they could be formatted into graphics symbols of different sorts or text or whatever you wanted. And a huge amount of evolution here in the communication. The early Unix systems really were just standalone, but to get around this initially, there was a Unix to Unix call processing the application developed by Mike Lesk that involved modem dial-up. So I was able to get onto the internet from Bell Labs by dialing up using UUCP to the Berkeley system, Unix system that was connected directly to the internet, and I could send email in the 1970s to anybody who had an email account on the internet. And this then evolved into support for TCP/IP and so forth today. The documentation for Unix, as we said, it was one of the first operating systems to include all the documentation online. So there are manual pages for each command, each library component, each system call, and there were longer documents that detailed major subsystems such as the C language or the text runoff processing system. The impact of Unix really can't be underestimated. It just is the standard, and it's continues to evolve. So if there is something that's better, Unix will gobble it up, and it'll be part of Unix. The impact that it had on other systems was it provided interactivity. The software was given to all of these schools at a nominal cost. So when people went out into industry, their companies would get Unix licenses, and then they'd start to build products using Unix, and then write things in C, and so it spread from the universities to the businesses. The file system that Unix had was dramatically simpler than a lot of other file systems out there. Just any file was always just a string of bytes, period, end of story. But a lot of times you wanted to do other things, and it didn't fit this simple model, and people came up with all kinds of interesting workarounds. So the hierarchical file system became really a standard that was popularized by Unix. Others had non-hierarchical file systems, but this seemed to carry the day. There was a command interpreter. that just morphed into all kinds of things. There wasn't, for example, IBM on the 360 developed job control language, and there wasn't any such thing in Unix. There were only shell scripts. But these were just another program here. There wasn't anything special about it. And so it goes. So that the simplicity, the fundamental simplifying assumption of Unix was its focus on text for nearly all file formats. There weren't any binary editors. Everything was configured using text shell command scripts. And so the common denominator in the I/O system was the byte, unlike the record in many other file systems. And this led to, made things incredibly useful and simple. And this alone carried the day. And the syntax that Unix popularized for regular expressions really found widespread use everywhere. It's the lingua franca of computers. The early Unix developers were important in bringing these concepts of modularity and reusability. The fact that you use something in different contexts made it far more reliable over time. And this led to this push for software tools. And there was a whole culture that developed with this. The TCP/IP networking protocols were implemented on Unix early on in the middle 70s, and they connected everything to everything, and that by itself helped to spread Unix. And then the policy of online documentation, and for many years there was an access to source code, which led to the launch of a free software unit movement in 1983 and open source type operating systems. So here we have just a list of Unix-like operating systems that you can see goes on. And if you look at these, you'd remember them from days of yore. The C programming language was, again, a procedural language that supported structured programming. It had a lexical variable scope. It supported recursion, which was huge, and there was a static type system, but it was designed to be compiled to provide low-level access to memory and language constructs. So again, you could do device drivers, and yet you could run cross-platform on this. So C became de facto something that came along with Unix. In computing, there's really two questions that come up. Does the data go to the program for processing, or does the program go to the data for processing? So this really results in the issue of address space in computers. How many bits are available to address any given item? Initially, memory was very expensive, and address space was 8 bits, then 12 bits, then 16 bits, then 32 bits, 128 bits today heading north. There's a statistical observation that occurred here, looking at thousands of application programs over years. The address space has to increase by 1.5 bits per year since the start of commercial computing. So it is what it is. The computer industry, in summary, has evolved over 8 decades. It's impacted virtually every aspect of daily life. There have been wave after wave of hardware and software technology advances, as well as just, I'll just say, things like going to object-oriented programming is a intellectual advance here. The underlying technology of hardware was built on solid-state electronics. The underlying software technology evolved into this object-oriented programming paradigm. And the internet started with 2 computers in 1969. And today, there's over 8 billion addressable nodes and heading north. So that's where we're at. Here's my short bio here. I spent 12 years at Bell Laboratories, which I talked about. I worked on over 20 different Unix application systems, and was pulled in as a consultant on another 80 and created a class for a master's level computer science program that was taught internally at Bell Labs for a number of years. And I've spent a lot of time doing independent consulting and venture capital. So thank you very much for the time today. And we will, any questions, please send emails to bartstock@gmail.com.